Excellent. Thank you very much for attending. So I'm going to talk about programming language design for GPU systems. And this is all kind of joint work with my PhD student, Bastian Köpke. So I'm going to start a little bit to talk about GPU systems, right? Because in this industrial forum here, it's like we have quite a range of topics to cover. And I think one excellent topic, if you're kind of a bit new to the topic of GPUs or like generally performance systems, right, is this keynote that Jonathan Reagan-Kelly gave last year at PLDI, where he gave basically an introduction of kind of the current state of computer hardware systems, right? Why are actually our computer systems like they are today? And kind of maybe also like what is the trend going to continue? I'm going to take the beginning of the talk a little bit to highlight the key points that Jonathan makes in the slides as well, and then come basically kind of to our solutions where kind of the language for these systems then comes in, and the need for research doing this. So one of the kind of astonishing facts that Jonathan points out is, right, that in 50 years of computing, we have managed to increase the energy efficiency by 1 billion times. Right, so the Cray 1 on the left, which was kind of known the first supercomputer, and it was phrased as this because it was so outrageously faster than anything of the time, right, had 160 megaflops, right, and would burn through 700 watts per megaflop roughly. In 2024, so last year when Jonathan gave this keynote, right, for the 700 watts, you would get this this board would give you like kind of 700 watts per petaflop, and this is kind of this 1 billion times of energy efficiency. And in some sense, like it's just, I mean, it's a number, but it's a number with a lot of zeros attached to this, okay? And at the same time, in the same time frame, right, the cars in 1975 looked pretty much exactly like the cars that still look today, okay? They were using a little bit more petrol maybe, but they were running the same order of magnitude of speed, right? We have not made 115 miles like 1 billion times faster running our cars. And the plane you might have come with to this conference like might have been literally the exact same plane that was already flying 1975, right? So it's kind of remarkable how much progress we have made in the hardware space to accelerate efficiency in computing. And if you look at today, right, our devices, like how we have achieved this energy efficiency gain, right, lies very much not in these kind of traditional computer architectures, right? But it lies in these kind of newer throughput-oriented architectures. Okay, so Jonathan puts up this slide where he says, like, if you take like standard Python, you run a matrix multiply, right? And you use GPUs or like these specialized, what they're called your neural processing units, right? That's the percentage of what you actually get out of the potential that this hardware device, right, this Apple laptop actually provides. So it means if you actually really care about getting performance out, right, you can get 6 orders of magnitude in performance difference, right, by changing computer architecture and how you program your devices, right? The same physical like block we are carrying around. And I'm going to talk about this kind of GPU layer, and you can see that this is still kind of far from giving us like the maximum peak performance. But in some sense, the GPU is an interesting middle ground between flexibility, so we can do more than just one op super efficiently, and still giving us much more performance than what like a traditional CPU might give us. So these, what I call traditional latency-oriented architectures, right, they have kind of driven kind of on Moore's law for a long time, and the goal we had set out for these was basically, let's reduce the runtime of a single thread of execution. Right? So in 1975 or even before, right, we had this idea, we write like programs, right, they run one thread of execution, and we said like, how can we make that faster? And for that, we basically investigated for a long time in 3 types of optimizations, right? Number 1, we increased the clock speed, frequency until we couldn't anymore, because in physics, like at the gigahertz rates that we are running today, right, the speed of light travels like 30 centimeters, like at these gigahertz rates, right? So we can't just increase the clock frequency. There's just physical laws preventing us from doing so, okay? And then people said like, okay, let's actually try to execute multiple instructions in a single clock cycle, right? If we can't make the clock cycles faster, let's do more stuff. That is what is called superscalar computer hardware. But we do this in hardware. So the software is still the illusion as if you execute just single instructions in each step, right? And then the third optimization was to say like, okay, actually we realize we wait a lot by stalling, right, our sequence of execution by waiting, for example, for memory, right? Or if we go down a branch, we have to kind of wait until we load the instructions, right? We can't load instructions ahead. So let's use speculation as a method, right, to optimize. And this is like either caches, right, and prefetching, but this is also branch prediction, all this stuff kind of. These are all this idea, right? Let's avoid that the hardware units become we are not busy. And the goal was always, let's optimize a single thread of execution, okay? And the big shift with these GPU and NPU architectures is to say, let's change the objective of what we are trying to do, okay? And that is what is known as throughput-oriented architectures. Because the goal is no longer, let's increase a single thread to go faster and faster, but the goal is, let's try to increase the overall amount of work we can do in a time frame, right? Throughput. And that is now different ideas, and these ideas kind of drive how our computer hardware architecture looks today, okay? Idea number one is, like, if we get more silicon because we shrink our production processes, right, what do we do with twice the amount of silicon? Rather than spending this on the ideas that we spent it before, so like control, like having speculation and this sort of stuff, right? We basically scale by having multiple copies of the same core, right? So we do multi-core, right? We copy over this down here, right? We copy over kind of our control, execution, caches, and so on, okay? Step number two, idea number two, trend number two is, right? If each of these individual like ALUs, right? So the instruction units that can actually do like an arithmetic operation, if that has their own fetch decode cycle, so it can decide independently what it does, right? Then that is actually quite expensive because we spend a lot of time figuring out what should we do next and decoding the instruction and so on, right? So the trend is if we do just one decides what we do and then an entire group is doing it together, SIMD style, right? Single instruction, multiple data, right? Then we can reduce the control overhead. And so we see kind of a big trend towards the SIMD execution on CPU but also on GPU. And then the last bit is, right, let's hide latency in a different way, right? So far we said we do speculation, right? So we do caches, we do branch prediction, that in hardware, that requires a lot of area and energy to actually do this. So let's kill this off of our chips, right? So we no longer do mega caches and out of order control. And we're just relying on the fact that we're going to have thousands of threads, right? And we must make them ready to execute immediately. And for that, we are basically now needing, right, much more space to store basically the state of these registers so that we can immediately flip from one register to, from one thread to the next. And that means on these GPUs, you see these huge register files, right, of a lot of memory, just so that we can quickly switch between threads to avoid stalls. Okay? So these are just in some sense, if you've never heard about GPUs, these are kind of the big trends that govern kind of this kind of architectures. And if you look at a concrete GPU, right, so the NVIDIA Blackwell GPU, right, at the bottom left, you see here a kind of overview diagram, right? All of the small green things are individual functional units that can do like arithmetic operations, right? And on the right, you see kind of one of these blocks, right? So one of these tiny blocks here, right? One of those being blown up, okay? Because in some sense, you can think of this as a 192 multi-core architecture. And each of these multi-core called streaming multiprocessors by NVIDIA SMs, they have 128 units that are axed in kind of groups of 32. So kind of they are scheduled in units of 4. This is the SIMD scheduling, okay? And then we have 65,000 registers, right, to be able to quickly switch between these different threads and hold all the state at the same time, okay? So these are just these three ideas kind of seen in concrete architectures. Okay, so the hardware is somehow amazing. Like when I see these diagrams and they just get like more fine-grained and fine-grained every architecture generation, right? It kind of boggles my mind how many parallelism, how many stuff runs simultaneously on these architectures. What an engineering achievement, okay? But the gap somehow between what I think, or Jonathan calls reasonable code, right? So it's somehow clean, people can understand it, it's modular, it's portable, the next generation will have similar performance, right? We can actually teach this undergrad students and they can find an entry and so on, right? The gap between this and getting actually the full performance out of this, like the gap is just like huge, right? And that's kind of maybe a problem, but maybe it's also an opportunity for us programming language designers, okay? And why does this gap exist? And Jonathan argues for this to say, like, the hardware has really radically changed, right? So this, what I just showed you, is not nearly anything that, like what this Cray 1 looked like. But the software actually hasn't largely changed, right? So we've seen basically kind of that in the programming models of these days, we still often usually think about, like, we have one unified global memory, right? Which is not true in hardware, but we're trying to pretend, right? We have sequential scalar primitives for building our computations, right? And we have abstractions to subroutines, pointers, and so on and so forth, right? So we're kind of pretending as if the hardware would be a PDP-11. This is Jonathan's slide, right? Not my observation. And then the software devices we have, basically, they are kind of like, was there anything else, right? And that, of course, like, is kind of a big problem, okay? And in some sense, and now comes the GPU-specific part of this, I argue this is kind of the same for CUDA, okay? So CUDA, which I like framed there as the first general-purpose GPU programming language, at least the first that went mainstream and made it kind of to production systems, right? This was released in 2006. This is now, next year, 20 years of kind of GPU programming, right? That's already like a huge time frame. And they released this based on this research project out of Stanford by Ian Buck, right? And he, in this video, which actually is fun to watch, this is from 2006, he says our goal is C on the GPU, right? So they built just now architectures that look nothing like the CPU, and they say like, oh, but this is the model, the software model that we should adopt. Right? And with that, I say, like, what a missed opportunity, right? So they adopted a model that was not made for this architecture, right? And then tried to make it work, okay? And they said this should be easy to learn for developers familiar with C, right? They are not familiar with having to manage 10,000 threads, but anyway, at least the syntax looks close, I guess, right? And basically all of the other mainstream approaches, like OpenCL, SYCL, like whatever the other vendors are doing, right? They follow basically the same model, which I'm going to call the thread-centric kernel programming model. I'm going to explain this in a minute, okay? And CUDA has kind of gained new features, but again, the hardware architectures of GPUs have actually evolved significantly with new features, asynchronicity, these tensor cores and other aspects, right? And like, they've been kind of poorly adopted or poorly fit into this CUDA framework, right? Because also, there is quite a bit of CUDA code out there, okay? Okay, so what's this thread-centric model that I've been talking about? So if you know GPU programming, this is like super like easy, right? But if you haven't, right, this is a function, right, that is going to be executed by thousands of threads simultaneously on a GPU. We call this a kernel function, okay? And what makes this a kernel function is, well, some annotations like this global there, okay? But the programming model, the mental model is that we're going to have these special identifiers, these block and thread IDs, okay? And they are going to basically be different, right, for each different thread executing this function. And so this function gets executed in parallel by thousands of threads, okay? But each thread you can identify by these IDs, okay? And then you use these usually, for example, to index into memory, which means every thread will index into a different location in memory. And that's how we achieve data parallelism. Okay. So if now, and how do we do the indexing? Well, C, right? Great idea, pointers, so dereference, so we just do explicit indexing, and that means these IDs are also they're basically just ints, right? I mean, in the CUDA abstraction model, they are literally just ints. And so that means if I'm now asking you, like, is this implementation of transposing a matrix correct, right? So does it actually transpose the matrix and won't fail? Then I'm basically going to have to ask the question, or I'm going to simplify this for you, right? Is this memory access safe? Okay? Which of course now means I have to think about, on the right, multiple threads executing this together. They are arranged in a two-dimensional shape in this case. And then I have my memory, which I've kind of laid out here also 2D. Of course, this is in reality kind of all flat. And so let's see. If the first 4 threads, right, of the first row there, if they access the memory, they're going to access the first row, right? That seems like I'm actually hitting the pattern of, right, I'm trying to transpose this matrix. But if I do this with the second, then I'm actually noticing, damn it, they actually do map to the first. And because I was writing in this position, I've created a data race, right? I have multiple threads, unsynchronized, writing to the same memory location. So what was the mistake I did? well, I forgot a pair of parentheses in my indexing computation, right? So meaning, this is of course a simple example. You can check this with testing and other bits. But, sorry. Let me see if this will fix in a second. But I guess you get my point that this is examples, right, that can get much more complicated and that can be very tricky to find in various situations, okay? So how can we maybe create a safe language, right? So a language that, where we maybe help programmers to prevent having these mistakes, okay? And there have been a series of languages being created actually that is safe, but most of them do this by being kind of very high level, right? So they are kind of taking decisions away from the programmer to decide which thread should actually touch which memory at which point of time. And we basically said we want to create a safe language that is also a systems programming language, meaning where the programmer remains in control of these decisions. Okay, because these are performance critical, because otherwise, why would you program this device? And so we have designed a language called Descent, okay, and the slogan kind of we go for is like, if a program is successfully compiled, so it passes the type checking phase, right, then we guarantee you that it's free of data races and, I call it, other memory-related problems, meaning particularly there's one source of deadlocks that can occur on the GPU if you mess your synchronization up, and we can catch those. And we can also have something to say about how the CPU and GPU actually interact together and making this a safe interplay. Okay, so this is the same function that we wrote in CUDA before, but now written in our Descent language that has been heavily inspired by, well, Rust, both in syntax but also in like the type checking part. Okay, so how do we write programs in Descent? Okay, so in Descent we are following. So at first, as you can see, if we go this from the top through, right, we have some annotations on these types, okay? So we adopt the same notion of unique and shared references from Rust. But we're adding to this like a notion of what we call an address space, which basically allows us to distinguish like what memory goes to the CPU, to the GPU, and on the GPU there are different regions of memory. And we're going to make sure that we are not messing up, like trying to access a piece of CPU memory from the GPU, right? Which CUDA doesn't do. And we also have the notion of multidimensional arrays, and we track their sizes like as part of the type, right? So to be able to statically guarantee that we are not having out-of-bound accesses, for example. Okay, and then besides these memory annotations, we also have an annotation on the function where we are executing basically who is allowed to execute this function. So we are being explicit about saying this function is guaranteed to be executed on the GPU by a grid, which is basically the dimensionality of how many threads I'm launching, right, that has this precise dimensions. And then, and this is crucial, right, we are not following this thread-centric model. Our mental model is to say this function is executed by this entire GPU grid, kind of together, right, as a unit. And then we basically hierarchically schedule down and say like, okay, if this block of code is executed collectively by the entire GPU, right, this is now the piece of code that is executed by the different blocks, so the different subunits, the groups of threads. And then inside these parts, these are now collected or executed by each individual thread in each block, okay? And this hierarchical kind of coming down from the top allows us to adjust the borrowing and ownership system from Rust to kind of pass on ownership kind of in a structured way down to the underlying threads so that we can ensure memory safety. And so how do we do this? Okay, so on the one side, it's this passing on these references down in a structured way. And then on the other way, it's this what we call views, which are basically a way to say to the type system, right, we have an array, right, where we have a lot of data, we have a bunch of parallel threads running, right, how can we map these in a safe way together, right, so that basically not two threads will get access to the same location. And for this, we have this idea which we call views. So this means the same thing that we looked at before, right, where we access kind of and wrote into this memory. We express this by the slightly grayed out term at the top, which we go through in a bit. And each of these things is what we call a view. So this group by tile is a view that transposes kind of your view, your understanding of how you look at the memory in a certain way. And then we are selecting into this view and saying like, the first block is now going to access exactly these orange pieces. Okay, and we drill in, and now we're only talking about those. And with this selection, we also pass on ownership down to the section, to this particular block. And then we continue this process to the threads, so that at the end we can guarantee that this one thread in this one block will exclusively own these two elements. Okay? And that ensures data race freedom. And we have these views here. They look very specific, group by tile, group by row. Okay, cool. But they are just compositions of these more fundamental underlying views. These 5 views are kind of baked in, right? These are safe mappings of safe ways to access multidimensional or multidimensional tensors. And by composition, we know then that also these views that we have just built as a library are also going to be safe. Okay. Okay. So memory access is now, I can guarantee you data race freedom, okay, but we also have sometimes need for synchronization. So particularly here in line 9, I'm writing to the temp array, and then in line 15, I'm reading from it. And actually, if you notice there's in line 9, this transpose in the view. So this means I'm actually writing a different, like the same thread is not going to read from the same location again. Okay, so I need a synchronization to make this safe. And if you write this code and give this to descent, you're going to see an error message. This will basically say, well, you're actually trying to access the same memory, right? But you're actually accessing a location that has not been kind of freed, that is still owned by somebody else. And so we are enforcing that you write the synchronization. We are not putting it in there for you because you have choices where you might want to put this, okay? But we are going to check that you have ensured it before you access the memory again. And then also, there are kind of certain problems that can arise when you are in the boundary between CPU and GPU. So you have CPU memory, GPU memory, and you don't want them to be basically access them kind of from the GPU, CPU memory and the other way around. And in CUDA, this can totally happen using these APIs up there on the top, right? And in descent, if you use these type of APIs wrong, or you allocate memory wrong, or dereference here the pointer in the wrong address, by the wrong execution resource, so meaning by the wrong like hardware unit, we will statically catch those cases. Okay, and similarly, one of these kind of slightly more nuanced bits is that CUDA code is often written like the one there at the above, where you just access an array with the index under the assumption that you're going to launch exactly as many threads as there are elements in the array. So you have an implicit assumption that this will not change. But of course, in reality, you might change your CPU code, right? Or you might change your GPU code, and these assumptions might not hold anymore. So on our side, we are basically going to enforce by having these execution resources annotated on these GPU functions, right? We're going to basically communicate these assumptions to the type system so that we can check them statically as well. Okay. Does this actually allow you to write fast programs? Okay, and the answer is pretty much yes. Okay, so we here have a version of different programs we wrote, right? And we basically see relative performance to CUDA, which is green, and our stuff, which is blue. We have certain small instances, like particularly the gem one, where we actually are slightly faster. This is just an artifact of the case that we generated kind of a loop that the CUDA compiler could decide to unroll or not. And in the CUDA code we wrote, it just felt very unnatural to write a loop there, and we unrolled it manually. And that actually led to this 10-15% performance benefit. Okay, but the point here is not what's the fastest version of these implementations. It's basically, can we represent the same optimizations you might write in CUDA again? And basically, yes, you can, and you get a similar performance. For this histogram, we use atomics, which I haven't talked about, but they extend kind of naturally into this ownership system, similar to what Rust does. And then maybe last, we have also looked at algorithms, like this graph algorithm, that require indirect memory accesses. So I'm loading an index from memory and then loading some data based on this. And that basically requires us to reason about, well, kind of data-dependent reasoning. And of course, we can't do this statically, because we can't guarantee that these indices will be inbound, right? And so we have a similar escape hatch as that you see in Rust, right? Where we can basically use the word unsafe to say like, the type checker or our borrowing checker will kind of bail out. And we did this for this benchmark suites in a kind of interesting way. There was kind of a CUDA library on the GPU, right, the GPU library for doing the single shortest path, the graph library, and we wrap this in an interface, right, so that we kind of hide the unsafe CUDA code there, and we could then still use this in safe code, and we just had to call into this library kind of, well, inside of this library, the code was unsafe. Okay. I'm not going to talk about how we actually achieve this, the safety, but there is a formal system and so on. You can read this in our PLDI 2024 paper, okay? And we have, well, as I said, like a formal type system, a GitHub implementation. We are currently working on actually mechanizing and formalizing this and trying to prove these properties that I talked about, like formally. The main thing that prevents us from doing this is having a good dynamic semantics of what GPUs actually do when they execute, okay, so that we can actually prove that these properties hold, okay. But anyway, I'll open this up for questions because then we have still a couple of questions for the audience. Thank you very much.
Great, we have 5 minutes for questions, so if you have a question, please come to the mic.
Hi, thank you for the talk. I'm wondering, what do you think is the path to adoption of Descent? Or do you think people should adopt it instead of CUDA, or is it sort of more of a prototype?
So, I mean, at the moment, of course, this is a prototype written by one PhD student, right? I mean, you're very much interested or welcome to look at our GitHub code and send us, right? At the same time, like, do not send us a billion pull requests or whatever, or like issue tracks or whatever, right? So, I mean, this is very much a research prototype, okay? It would be lovely to adopt some of these ideas in real systems, okay? In particular, I think what I found very encouraging was that the feedback we got at PLDI from the reviewers was, hooray, finally somebody is doing PL research in this space, right? And I think that actually is, for me, possibly kind of the biggest impact, is to say, like, well, go out there and design other systems and get ideas. We are talking with people like in industry, right, about these ideas and seeing like where they might be adopted. I think one aspect that is a bit tricky is that we care a lot here, right, about race freedom and deadlock freedom and so on, right? But there were no good tools. There were some tools, right, but not perfect tools for checking these things already. And in industry, people basically do not use them much because A, the hardware keeps changing very quickly. So it means we are not actually modeling what's current. And B, they have reasonably enough testing infrastructure to catch this stuff. So I think one thing that that is here, the question is like, are we actually solving the problem that most GPU engineers are having? But I think it would be interesting to follow this work up with maybe can we also give more performance guarantees? So we guarantee you that, I don't know, you get core-less memory accesses, or we are guaranteeing you other bits, right? So I think this is kind of a starting point, hopefully, for more research to impact kind of industry adoption kind of mid-long term.
Cool. Yeah, great. Thanks.
Hi. Thanks for the very nice talk. I'm interested in reasoning about Rust programs, but now I'm also interested in reasoning about Descent programs. Yeah. So I wondered two things. Have you thought about whether the type system can be used to support verification of programs in terms of what they actually do? Mm-hmm. And I guess complementary to that, where you use unsafe code, have you thought about how you would prove that the unsafe code is actually okay? Yeah.
Okay, I mean, verification, functional verification is kind of not part of our story at this moment, okay? Bastian, my PhD student did an internship just now with the RISE group at Microsoft, and they're very much interested in using separation logic and other bits to actually be able to also reason about functional properties of the programs, right? If you want to reason about the unsafe CUDA code, well, then you have to somehow think about how do you do this, right? So what's your semantics of CUDA programs and so on. And I think if you would have a good semantics of CUDA programs that would be up to date, that would be very useful for a lot of tools. But I think that would be a massive undertaking that at the moment at least doesn't exist.
Okay. Thank you.
Cool.
Okay, so if your goal was to sell NVIDIA GPUs for programmers, C would seem like a good choice back then, right? Now, about your language, how does it deal with GPU portability? Because as you said, new models have different memory structures and so on. And there are things like the interleaving or memory banks and some low-level things that are GPU specific. Can your language somehow add features to model those or safety on those?
Great question. So at the moment, we model basically a very kind of, in some sense, like basic understanding of what GPUs can do. But at the moment, I would claim that this is fairly portable also to not NVIDIA hardware. Okay. But I think you're touching on a point that I find super interesting to kind of go next, right? Because the hardware keeps changing so fast, right? How do we actually, what would we do to evolve these languages at the same pace? So I'm having a system that gives you all the guarantees, right? NVIDIA develops a new hardware device. How long do I take to adjust my type system to also count this? Yeah, that's exactly one of the next topics I would like to look into, but I don't have a good answer for this yet. If you have ideas, I would love to hear more.
Okay. Just a side note, I wonder whether you could compile TensorFlow or PyTorch to descend instead of...
This is also one of the interesting aspects for us to look into, but we haven't done that so far.
Can be very short one.
Yeah, very short one. Great talk. What's the expressivity of the tensor access operations relative to affine indexing?
So you mean these views that I talked
Yes.
about, right? Yeah, I don't think we have a fully formal understanding of what we can actually represent with and what not. My intuition says me that I think we should be able to do most affine stuff because they map very naturally to this, right? But at the same time, I can't give you a formal guarantee. So
Thank
I
you.
think this would be interesting to explore.
Okay, great. Let's thank speaker again.
Thank you.
And